Poliak, who is finishing up his PhD at Johns Hopkins, advised by Benjamin van Dorm. And his area of research is natural language processing, and he has won some Best Paper Awards in that area, as well as having been a GEM Fellow and done some work at Bloomberg and MIT labs. And he's going to talk to us today about his work exploring reasoning capabilities in natural language processing models.
So I'll first start by defining what is natural language processing. Focus more on this side, sorry. And here we're going to take this idea, this definition, that NLP, or natural language processing, broadly aims to develop systems that humans can interact with through spoken and written language. So we have systems like Amazon Echo, Siri, Google Translate, and Grammarly that we interact with basically every day, and they're ubiquitous in the world, and they work really well. However, when they fail, they sometimes fail really poorly. So this is an example about a month ago that I actually discussed in my AI class, where Facebook apologizes for rude mistranslation of Xi Jinping's name. And this is what happened. I put up expletives, where so the Chinese president was visiting Myanmar, Burma, and the Burma State Consular Office welcomed him to China. However, when Facebook automatically translated that into English, it got his name wrong, calling him asshole. And it did that a lot. So really you can see here that even though these systems are ubiquitous and out there, they're still making a lot of mistakes that have big consequences. And the real pitch is, and the reason why I think it's important to explore the reasoning capabilities of natural language processing models is because if we want to improve our system's ability to translate, we should understand where they fail. If we want to improve our system's abilities to summarize text, we should understand where they fail. If we want to improve their ability to spell check, we should understand where they fail. Basically, anything that we want to improve our NLP system's abilities to do, we really need to understand where they fail. And this brings us to our outline for what we're going to speak about today. So we're going to discuss tests that I've developed that help us analyze the inference capabilities of these systems. We'll talk as well about discovering biases in existing tests that people have been using for a while. And we're also going to finally conclude with issues to overcome biases in data and then apply these types of lessons to real-world use cases. And this is what would bring us to natural language inference. So natural language inference follows the long tradition in NLP based on linguistics, where using this task, often sometimes referred to as recognizing textual entailment, as a way to evaluate our model's reasoning capabilities. And what this task is, you're given a premise, such as Millie ran across the quad. We have a little bit dolls. And in a hypothesis, the mascot moved. And the goal here is to determine whether the second sentence hypothesis is entailed or not entailed by the premise. And this isn't a strict logical entailment, but it's some fuzzy notion. So here it's basically saying, would the second sentence hypothesis be likely inferred by the first one of the premise? So what would this example be? I think this would be an entailed or not entailed. Yeah, Dale's saying yeah. Sweet, exactly. It's entailed. And the reason why is because Millie is the mascot here, Barnard, and if she ran across the quad, then she moved. And historically, to provide some context for this task and how it's been used in the NLP community. So in the 90s, there was this large consortium of linguists in Europe who came up with this data set called Fracas. And what it was a data set to determine whether models perform distinct types of reasoning. And what these linguists did was they basically hand-wrote lots of examples for different phenomena. And if you give a linguist a lot of money, they'll create great examples, but not that many. So this had about 300 or so examples. Then in the mid-2000s was the Pascal recognizing textual entailment challenges. And this was a generic evaluation framework to compare models for distinct downstream tasks. Because the problem they had was they had these systems to do different things. They had systems to translate text. They had systems to summarize text. but they had no one framework to evaluate the reasoning capabilities of their models. And some of the data that they actually used initially in some of these recognizing textual entailment challenges came from across the street, where Kathy McEwen and one of her students, Regina Barzilay, who's now faculty at MIT for a while, had this data set on multi-document summarization, and some of the data in some of these earlier Pascal recognizing textual entailment challenges came from that as well. So more recently, we have the Stanford NLI and multi-NLI that was developed downtown at NYU. And these are large-scale data sets. So Fracas was at 300 examples, and the RTE data sets had about 5,000 to 10,000 examples each. These had 500,000 examples, so they're huge. And they've been used a lot to evaluate the sentence representations that are learned by neural models. And they've also been used to train and improve models for downstream tasks. So before we talk about issues with some of these data sets, we're going to look at how do we build computational models, primarily neural networks, to do this task, to perform this challenge. So this is what a typical NLI model does. We're going to go into this a bit more detail. And the goal here is to be able to build a model that can take these as input and correctly predict this output of entail, make this prediction. And this is exactly what this would look like, where we would take our sentences, independently pass them through this network, and we'd expect to say entailed. And we're going to walk through some of these steps in a bit more detail, starting with word embeddings, sentence encoders, and multi-layer perceptrons. And the big question is, we can't just feed a computer these sentences, because we might be able to read English, we know how to read this alphabet, but computers don't. Computers basically just read numbers. So what we need to do is we need to come up with a way to represent these words in a way that a computer can actually read them and perform some mathematical operations on them. So the first approach is called one-hot vectors. And what this is we just basically have a unique vector for each word, and all the values in the vector are 0, except for 1. And the value, basically this would be an indicator vector of which word is being represented. So if we look this out for our sentence, we could see here is basically the columns represent the vector, represent each position in the vector. And we can see that all of these columns are 0, all of the values are 0, except for here would be 1 to indicate that that's for the vector for the word across. So then here the rows become our words. And some issues with this is that these vectors are going to be very long. They're going to be the size of our vocabulary. And additionally, the big issue is so what we can do actually is, let's convert that right here. So we see one issue is that these vectors are going to be very long. Why else might we not like these vectors? What else might be bad about them?
Doesn't represent any relationships.
Exactly. There's no meaning. The meaning of the words isn't preserved. Where when we read the sentence on the right, and that's got moved, we can understand what each of these words mean. But when we represent words with just one-hot vectors, we're not going to capture that. There's no way for our models to initially capture the meaning behind these words. So in linguistics, there's this notion called distributional hypothesis. And what this is saying is that words within similar contexts share similar meanings. And Firth has this famous quote that's, "You shall know a word by the company it keeps." And in essence, what this is saying is oftentimes we can figure out a meaning of a word just by the context. And if we know that the same word has similar context, then that can indicate that these words have similar meanings. So what we do is basically try to come up with vectors that capture this notion that similar words appear in similar contexts. So what we do here is basically, this is a very simple model where we're given a representation of a word T. The goal is to predict the context. There are also the flipped models where you can, given a context, predict a word. But for right now, we're just going to focus on this. And really, you're going to basically, by doing this process, forward and backwards, you're going to update the vectors that we have for W. And if we ground that out in an example, this now would become like the vectors for each of these words. And unlike before, where the dimensionality was very large of the one-hot vectors, these become much smaller. And that's why word embeddings are often called like low-dimensional vector representations of words. And in fact, models like Word2Vec, which we look at graphically, have been shown to preserve a lot of word meaning. So people have looked at analogies and shown that there's some relationships between words are actually captured by word embeddings. I've spent like a lot of work actually working on this in terms of how can we come up with newer methods to capture these words, how can we encode more information besides for just the words around it. But we're not going to focus on that now, and for today we're just going to basically use this as our setup for word embeddings. Now we've discussed word embeddings, we're going to figure out how can we're going to talk about sentence encoders. And what we're going to try to do with a sentence encoder is try to encode both of these sentences to get representation based upon the single word vectors. And that's right exactly right there. So if we look at a neural network right here, this is like a very simple, basic neural network with one hidden layer and one neuron. Right? And what we can see is that we have an input, which is fixed dimensions. So here is a dimension of 4, and a fixed output of just 1 dimension. And mathematically, what this is doing is basically this formula, where we are going to multiply our input by some matrix, pass that into a function, and then predict an output. And this W is what these weights are right here, and this is basically what is learned. So in neural networks, the goal is to learn a good W, to learn good matrices. So if we look back at our word embeddings, and we try basically putting these sentences into our neural network to make our prediction, what do we think is going to happen? Will this compute right here? And another way that I can ask you that is if we even convert them, what looks to be the issue here?
Not enough neurons.
Sorry?
Not enough neurons.
One neurons, right? But let's look even lower. Right, yeah, exactly.
Yeah.
Yeah, and where exactly? Yeah, there are not enough neurons here in the input. Because here, this is an input of 5 words, and on the right, it's an input of 3 words. But we've learned a matrix that's specific to 4 inputs. So how do we deal with that? And this brings us to recurrent neural networks. And we're going to focus in by zooming on just on one cell within the recurrent neural network. And what we see here is basically we pass in as input our xi, xi represents the ith word. So we put in one of these words. And we would also take in the input from the previous recurrent cell. And in essence, we'd be computing these functions. And we'd be basically computing these functions in order to generate a new state, a new hidden state, as well as a new output. And if we unroll this out, we can get something here, which is in essence a recurrent neural network. Because what we're doing is we're rolling out each of these cells in order to accommodate the length of our sentences. And then in essence, by rolling out these cells, we can pass in arbitrarily long sentences. And we can, in turn, after doing that, we can now get a fixed sentence representation all the way at the end. Right? And what you're doing, this is basically the formula for how you would compute that, because here you're basically passing in over and over and over until we get to the end of the sentence. And exactly S5 is a fixed representation. And then here we can also make them bidirectional. So here on the first layer, we're passing everything to the right. What we can do afterwards is now pass everything to the left as well. And then at this point, we can combine these two to create a fixed sentence representation. So in turn, we've taken these arbitrarily long sentences, and now we've converted them into fixed point representations. And that's what recurrent neural networks do. So the last thing we'll focus on technical details is the notion of multi-layer perceptrons. And because what we want to do at this point is we've combined these sentence representations right over here, and we want to make this prediction. So we go back to our single layered neural network. This is like exactly what it looks like. But we can design this further and basically stack hidden layers as well. And here we see that each neuron in a hidden layer is connected to the neurons of the next hidden layer. And in essence, in a multi-layer perceptron, this is what you're computing. Because the first thing we're computing is the first set of matrices, and this is going to be the matrices to convert our input layer to our hidden layer, first hidden layer, as well as a second set of matrices in order to convert from one hidden layer to the next, and so forth. And in a multi-layer perceptron, these functions, so neural networks in general, these functions are what we can specify a priori. And in a multi-layer perceptron, these functions are often nonlinear, and this allows us to be able to deal with data that's not separable, that's not linearly separable. In essence, this is like an overview of the typical modeling approach. So let's step back again and remember that so natural language inference is primarily used as an evaluation framework. So we talk about issues in existing frameworks. And these are three of the characteristics that we're going to talk about that make the prior data sets and the prior work really not really inefficient or maybe lacking to really solve this grand goal. And the first one is they don't provide much understanding in terms of our model's reasoning capabilities. So here we can see a graph of how some models have performed on Stanford NLI over the years. And we can see that accuracy is improving steadily, but yet this doesn't really help us determine what type of reasoning are our models performing. We have this number, but that won't help us understand why did the machine translation model mistranslate the Chinese president's name. That's not going to really help us. The second issue is how these data sets are often generated. They're very expensive to train. They require a lot of money or dough. They lead to types of biases. Some of these biases are stereotypical biases. These can be like race-based or gendered biases. And they also lead to class-based statistical irregularities, also known as annotation artifacts, and we're going to deal with that in detail a bit more later. And the third characteristic is the ones that do provide insight and are good probes are small. So as we mentioned before, Fracas contains about 300 examples. And these neural networks require a lot more examples to train on. And this then leads us to the Diverse Natural Language Inference Collection, or DNC for short. Right? And now we'll talk about this DNC collection in more detail. This was work that I presented at EMNLP in Brussels in 2018. And just one thing to note, so I want to highlight Edward who at the time was an undergraduate junior, who had just switched into computer science from cognitive science, and he worked on this project as well. This is the type of work I think is really great for undergraduate researchers that can introduce them to computer science research as well. I also want to point out Aparajita Halder. She was a visiting master's student from India who worked on this as well and whose master's thesis I supervised. So the DNC is a large-scale collection of diverse NLI problems. And what we did here is we basically convert existing reasoning tests from prior data sets into natural language inference. And to get a feel of what this is, these are some of the examples. So here we have the NLI data that's focused on puns. So the first sentence represents the premise, and the second is the hypothesis. So here the example would be, Kim heard masks have no face value, and that would entail that Kim heard a pun. Masks have no face value is a pun. And the thinking of this goes is that if your model can perform well on this subset of the data set, that might indicate that the model's performing some type of reasoning, or at least these vector representations are capturing some information about humor and puns. And this is the DNC as of 2 years ago. At that time, it had over half a million examples, so it's on the same exact scale as SNLI, and multi-NLI, and it's even bigger. We've been adding to it a lot. This is where you can find all the data. It's easily accessible on GitHub. And here you can see some of our additions to it, where we've added data to it that focuses on different function words. So it's how well do models capture prepositions or WH words. This was based upon a paper we presented at StarSem in 2019, and actually won the best paper for that as well. On the bottom, you can see there's a gender parity score. So one of the aspects of the DNC is there's a targeted data set that focuses on gendered pronoun resolution. So it's how well do models capture pronoun resolution, how well can it identify pronouns and match them to the people it associates with based upon the gender. So a big portion of this DNC and how we create this is this method of recasting. And what we're doing is we're basically leveraging existing annotations to create NLI datasets that probe different types of reasoning. So we take existing resources and we recast them into creating these focused evaluation datasets. And the real work here is really about recasting, where each of these datasets have their own issues, own idiosyncrasies, own details that make this process hard. But unfortunately, because of time and I get to a lot of other interesting stuff, we're not going to focus on these details right now, but I'm happy to talk about that offline. And I have additional slides as well that can explain how we went through some of the more difficult data sets. And to walk you through a few more examples, some of the phenomena that we capture is like event factuality. This is a linguistic phenomena of determining whether an event described in text actually happened or not according to the person who stated the sentence or the text. So here for the second example, we'd have the sentence of all need to ponder. This would not entail the sentence that the pondering happened. And part of this work is really a call to the larger natural language processing, computational linguistics community. And part of the call is for dataset creators, for people who are interested in specific types of phenomena to convert their data into natural language inference. In addition to the work from this past summer, it starts in 2019, I'm currently working with a sophomore who she is taking tweets that have been labeled as offensive or not and converting them into natural language inference as well. We're going to be competing in these like shared tasks in our community, offered for just like 70 now, and there's one coming up focused on offensive tweets, and we're actually going to be using that to compete as well. And actually, this work really has been picked up by the community, where this is a research group at an Indian university that has now created a Hindi-type version of this, and I believe it tests for phenomena like sentiment, and I don't remember the rest as well. And the second call to community is, now that we have a great resource like this, let's actually use this to test your model's ability to capture different types of reasoning. And that's what we're going to focus on for the small last part of this portion. So we're going to focus the task that we're going to choose here to look on. We're going to look at models trained to do translation. And what this task is just simply given text in one language, translate it in another language. Any two pairs that you're interested in. And here are some examples. There's Google Translate, Microsoft Translate. There are lots of commercial products out there as well. And one of the reasons why I really like machine translation and start with machine translation is because of this quote from Philip Cohn, who wrote the textbook on machine translation. He writes, "Researchers in deep learning often do not hesitate to claim that intermediate states in neural translation models encode semantics or meaning." And what he means by this last line here is basically there's a lot of hype in the machine translation research community. He's saying that these people who develop these new systems to do translation make claims that their systems understand language. So just to be like scholarly and correct here, when Philip writes this, there are no citations, and I looked through all the possible papers he could be referring to. None of them actually make these claims, but if you look at, a lot of these papers came from industry labs, and if you look at the PR press releases associated with these papers, these claims are in there. So I guess you have to be careful, but yeah.
If I can add, I've certainly seen talks, not necessarily in translation, but in other deep learning where they do say like, and you could like envision, especially like that, and you can see at the lower levels they're getting, you know, edges, and then it's animals, and then it's scenes, and you know, so it may not be fully in their paper, but it is, I think also that they at least imply such.
Yes.
They like to imply such claims might be true. They like to set that idea.
Yes. Yeah, exactly. Yeah. And then since this is recorded, I'll leave like more apparent to myself. But I have a lot of opinions on that. And this was really the question that I asked in this paper in NACL 2018. And the question is okay, great, machine translation researchers, let's call this out. Let's see, do your systems capture different phenomena that are important for translation? And this is exactly what we used a variant through the DNC for. And what are some of the types of reasoning we want in machine translation? And here are two of them. One is anaphora resolution, and one is paraphrastic inference. So anaphora resolution is just basically linking pronouns with their reference in text. So here we have a sentence, the father fed the child because she was hungry. And say we want to translate that into Spanish. How should we translate the word child? Niño or niña? I said niña,
but I can do this one.
Exactly. So if you chose niña, you're correct. And how come? Why would this be niña? Because she refers to the child. So, one time I gave this talk in November, and I'm like, let's look at Google Translate. Does it get it correctly? Then it did, but when we wrote this paper in 2017, it failed. So I would like to take credit for this change in Google Translate, but this might be just more of a correlation than a causation. And there are people in machine translation that have developed other tests to look for these types of issues as well. The second type of phenomena, or type of reasoning we want our systems to capture, is paraphrastic inference. And this is basically identifying paraphrases in text. And we can ground that out as an example. So we have this sentence. The father fed the whippersnapper because she was hungry. I'm not going to ask people if they know what whippersnapper means. I don't want to age anyone out. But this is, if you haven't been reading literature from the 40s to 60s, you might not know what the word whippersnapper means. But thanks to thesaurus.com, we know that whippersnapper is a synonym of child. And since we know how to translate the word child, our large MT system, maybe we might just want to swap in and try to translate the word child as opposed to whippersnapper. And there was a lot of work in natural language processing, and specifically this issue. People wrote PhD theses in the mid-2000s about this. So great, we identified the phenomena we want to test for, whether our machine translation systems. So now we'll talk about how do we actually go about doing it, what's the framework. And this picture here basically demonstrates the framework we're going to be using. And we'll walk through this step by step. The first step is we train a machine translation model. The type of model that we're going to be training is a neural machine translation model, where here, these are going to represent each like R and N cells. So here we're passing our text into a neural network in the green, and then here in the yellow, we want it to translate into another language. Next is we extract sentence representations from these trained encoders. So basically, in the previous step, we've learned these matrices. And in the second step, we're holding the matrices fixed, where we're going to use them. We're going to basically multiply the word embeddings for our premise and our hypothesis by these learned matrices in order to create sentence representations. And finally, we're going to be using those sentence representation to train a classifier on these subsets of the DNC. And this, in essence, is an overview of it. And what the goal here is that this framework, if the sentence representations capture these phenomena that we want the machine translation system to capture, then they should do well, then the classifiers should do well when they look at just those features. And for those who are interested in some more of the details, the specific type of neural machine translation model we use is a bi-LSTM encoder-decoder. This is just a fancier RNN that we discussed. And we look at 4 machine translation systems. We have all of our systems translate from English, but one of them translates into Arabic, Spanish, Chinese, and German. And now we can look at our results to see how well did each of these machine translation systems capture the phenomena. So we'll walk through this right here. So here on the right represents a model that was trained fully end-to-end on this task of paraphrastic inference within the DNC. And here what it means is trained end-to-end means that we're updating the representations of the sentence encoders. So this could sort of be viewed as an upper limit for how well our classifiers trained on machine translation encoder can do. In green, this light blue represents the majority baseline. Majority baseline is it's like a baseline where you're choosing at random, but what it means is basically you just choose whichever label you saw the most often during training. And that's why this is a little bit above 57%, and a little bit above 50%. If it was fully random, it would probably be around 50. And here we can see the models for each of the different, the neural machine translation encoders that were trained as a system to translate into these different languages. And what we can see here is that all of them perform worse than the majority baseline, indicating that these features might not actually capture this phenomena that we want them to. And something else that's interesting to note about these results is that we can see that the output language affects the representations that are learned, because we can see differences in the encoders that were trained as systems to other languages. And we have very similar results for NAFRA resolution as well. So in summer 2018, I was part of a large collaborative group that was hosted at Hopkins as part of these large JSALT workshops, where the research agenda for this 10-week program was to look at sentence representation learning. And the sub-team that I was on focused on identifying and probing for whether these representations capture different linguistic properties. So as part of that, I basically used the DNC to evaluate models that were trained for different tasks. So the colors on the right represent different tasks. The dark blue on top refers to, it's called grounded vision and language. So it's basically having models that can associate text with the items in a picture. We also looked at syntax. So this is basically, given a sentence, can your model now either give like the syntactic part of speech tags for each of the words, or can you develop the whole syntactic grammar, like a parse tree of that sentence. And on the bottom shows different, the DNC subsets that we focused on. But this I think is the most interesting, where we can see that really there are variations in how well the different models for different tasks capture different phenomena. So now we'll move over to discovering biases in existing tests. And what we're going to look at, this is an outline for how we're going to investigate dataset biases. So this is the question of the existing datasets already that have tests, but are there biases in there that might be another reason why we might want to use them? So for this, I'm going to introduce what we refer to as hypothesis-only natural language inference. And this is a modified version, where you're given a hypothesis, such as a woman is sleeping, and you're given an empty premise, and we're going to change it up a little bit. Instead of entailed or not entailed, we're going to make it a three-way classification problem. So now the question becomes, is this hypothesis entailed by an empty premise? Is it neutral by an empty premise, like not entailed or not contradicted? Or is it contradicted by this empty sentence? And their puzzle looks, because I agree that this might not necessarily like make sense. Like, how can we take a task that specifically, can one sentence follow from another and change it like this? But if we forced you to choose this, you really should just be guessing at random, right? So what do people think this sentence would be? How many hands for entailed? This would be entailed, no one? Would this be neutral by an empty sentence? We got one. We got two. We got contradicted by an empty sentence. Okay, so we got two listening.
I think I lost the logic of what implies, what we're being asked about.
Yeah, exactly, and that's part of that exactly is, I think, what makes this question so weird or bizarre and interesting as well, is that how can I ask, if I forced you really to ask, is this sentence entailed by another sentence that's hidden that I didn't give you? Like, what are you asking? It gets a question, what does that mean? And if I really forced you to choose, you would just be choosing at random. Right? But if you chose contradiction in this example, you would actually be right most of the time for this data set. But for this portion, we're going to hopefully be able to answer the questions of why is that a contradiction? Why is a woman sleeping a contradiction here? Can a model pick up on this? And if it can, like, what does this say about this task that's supposed to be this grand test? And what does it say about the data sets that we use for it? And in particular, we ask this question of, do natural language inference data sets contain statistical irregularities that allow a hypothesis-only model to outperform each data set specific prior? And this is work I presented at StarSem, Computational Semantics Conference in 2018, and we received a Best Paper award for this work as well. So now I'll talk a bit like the model that we're going to use for this. And this should be basically a review of what we've seen so far, where this is a typical natural language inference model. Here, an hypothesis-only model, we basically just X out the premise and don't consider it. And in turn, we end up with something like this. And we're going to use the same exact setup as we saw before, where we are going to convert our sentence, the woman was sleeping, into word embeddings, pass that into a sentence encoder to get a fixed sentence representation, and then pass that sentence representation to a multi-layer perceptron to either predict like this yes, no, or maybe. And now we'll talk about the data sets that we explored. So we broke them down into three different types of data sets. The first is recast, which we spoke about briefly before. We looked at 3 recast data sets. The second type is human judged. So what human judged is basically a human was given these 2 sentences, a premise and hypothesis, and the human wrote down, crowdsourced workers just wrote down the label. But what we're going to talk about most is about human elicited data. And when I refer to human elicited data, what I mean is this, is that a human, in order to create this data set, a human or a crowdsourced worker was shown the premise and was asked to generate a hypothesis for each of these, for each label. So they were asked, generate a hypothesis that's entailed, one that's neutral, and one that's contradicted by this premise. And this was used for SNLI and multi-NLI.
How confident are you that people who aren't, natural language processing researchers really understand the notion of like whether this sentence entails that sentence as opposed to just, it's true, it's not,
Yeah. So this is, I think, also like an interesting point about this work in general, is how do we convert, basically how do we explain these types of things in layman's terms so that crowdsourced workers can understand it. And oftentimes the definitions are then, are written down in a different way. And this is something that's actually, I think, very interesting, is when we compare different data sets and we look at what were the prompts and the definitions that different crowdsourced workers saw, we can see that they're not standard across the community. And then this creates a big issue of how do we have models that can generalize across different data sets, and that's something we're going to get to at the end of the talk as well. So let's do this as an example. Let's imagine we're a crowdsourced worker, and we were shown this premise, a woman is reading with a child, and we were asked to generate a hypothesis that was contradicted by this premise. Anyone want to give examples of what how they would do this? What would you write as a hypothesis that's contradicted by this premise?
No women exist.
No women exist. That definitely would be one thing that would not entail from this one. But exactly. Samantha's listening. Exactly. A woman is sleeping contradicts, but so does that other sentence. Exactly.
But how is it, sorry, a woman is sleeping, another woman is reading with a child. How does
Right.
that-
Exactly. So, and now exactly you're picking up on this question.
So it has to be the same.
Yeah, no, but that's exactly, I think, a really important question that you bring up, is that how, something that's overlooked by most people in the field, and if you read any of these papers, is what are the underlying assumptions we're making? Are we assuming that both of these sentences describe the same event? Are we not? And in the papers that I'd say are like higher quality, at least in the appendix, are going to describe these assumptions that are made. And in Stanford NLI dataset, in their appendix, I don't know if it's in the appendix, or definitely at least in the instructions showed to crowdsource workers, which they include in their paper, they made that assumption. So they said that these should describe the same event, same scenario. So now we're going to talk about our experiments, our setup, and the results that we found. And the setup here is just simple. We train a hypothesis-only model on each of the 10 data sets that we considered. Then we test the model on each specific data set. We're not doing anything like training on one data set and testing on another one. We're keeping models specific to the data sets that they were trained on because we want to identify whether there's this bias inherent in the data set. And to do that, we compare the results, which is the accuracy of the hypothesis-only model, to the majority baseline. Because really, if there's no signal in this data when you're only given one sentence, which there shouldn't be, you really should just be making the prediction that you saw the most during training. And these are results across 10 data sets. It's pretty large. Oh, this is like a nice big screen, so you probably can't see it all. But don't try straining your eyes. Here are the one thing to note are these blues. So blues indicate when we saw large increases over the hypothesis, over the majority baseline. And what we're going to focus on for now is really the Stanford NLI dataset, where we can see that the hypothesis-only model did more than twice as well as the majority baseline. Where majority baseline is like 30, or we'll go through that in more details. But the question to ask is what's enabling hypothesis-only model to do well? Is this some statistical irregularity in this data? Or is this maybe some background knowledge about the world or the data in of itself as well? So this is the results on the human elicited data, where the majority baseline on SNLI is 34 and multi-NLI is 35. Even though these are supposed to be balanced, there are a few examples where they're not. There's some premises that have like more than 3 contexts, so that's why we don't exactly see 33. And here are the hypothesis-only results, where we can see basically the hypothesis-only model does more than twice as well the majority baseline. And let's talk now about the origins of this data. Where did this SNLI data set come from? And it came from Flickr, where there was this data set released by Young et al. That had basically paired pictures from Flickr as well as captions, where the task that Young was interested was, given an image, can a computer system generate a caption? And the captions are what the SNLI was used in order to use as their premises. And if we look at Flickr, the types of pictures that we see on Flickr are people doing actions. If it's someone sand surfing, pitching a ball, driving a race car. And if we go back to our contradicted example of a woman is sleeping, we're not going to see this picture on Flickr. Like, you're not going to take this picture and it's just like creepy. You're definitely not going to be posting this on Flickr. So it might not be so surprising why we see this as a contradiction. And let's look at what are some of these premises that crowdsourced workers were shown that they were prompted that then they wrote a woman is sleeping as a contradiction. So we have a sentence like, a woman sings a song while playing piano, she's not sleeping. The woman is laughing at her baby shower, ain't sleeping. A woman with glasses is playing Jenga. She has dark glasses on, so maybe she wants to be sleeping, but she's definitely not sleeping here. So a question we need to ask is, why is she sleeping all the time? Because, as Roko mentioned, there are other examples, there are other sentences that people can give as contradictions. Why is it that she's sleeping all the time? And for this, we can look in cognitive science. So in cognitive science, it's known that studies in eliciting learning data are prone to repeated responses across subjects. So there's famous work by McRae et al., these are cognitive scientists in 2005, and they did this study. They asked people to come up with like descriptions of dogs. So think about for a few seconds, what are things you would think about when you're describing a dog? Look at that. So some of you might have said things like barks. Some of you might have said has a tail. You might have said furry. But none of you said larger than a tulip. And you probably definitely didn't say moves faster than an infant. And what McRae writes is basically that features such as is larger than a tulip or moves faster than an infant, although logically possible, do not occur in human responses. Because people are capable of verifying these facts, but they're not just going to give it. They're going to be giving it very similar things over and over again. And that's exactly what this idea is, that studies in eliciting norming data are prone to repeated responses across subjects. So if we look back at the origins of SMLI, this might actually explain why she is sleeping all the time. So given this, we will now ask, okay, now we know that, fine, the woman is sleeping, why this would be a contradiction oftentimes, but can we, from our data, infer the labels by just looking at a single word in the hypothesis? So what we do is we basically compute this conditional probability. In natural language processing, we're very good at doing this. We do this often. It's like a first step that you do with your textual data, and it gets you pretty far. So with this conditional probability, well, what's the probability of a label given a word, single word in the hypothesis? We say if it's larger than an alpha, then that's a giveaway word. And we look now at different types of words that are correlated with contradictions. So some of the words that we look at are sleeping, words associated with sleep, like sleeping, asleep, sleeps. The second set of words highly correlated with contradictions are negations and absolutes. So this is things like nobody, alone, no, or empty. And the last set of words highly correlated with contradictions are referred to as like motherly advice or sage advice, where these are words like driving or eating. And these are things that you shouldn't be doing if you're doing anything else. Right? You shouldn't be driving and texting. You shouldn't be eating and running. And it's important to note that there was a lot of concurrent work in the same time that discovered these similar issues as well. Two differences between our work, my work, and these two papers, besides for the award we got, is both of these only looked at 2 data sets, while ours was much more expansive, looking at 10 data sets. And this work really had an impact in the natural language processing community, where people are really opening their eyes and starting to ask questions about data sets and tasks that we've sort of taken for granted. So a few months after our work was published, this work from a group at CMU received the Best Paper Award, where they did the exact same thing, but on a reading comprehension data set. So this is a task that's similar to like the SATs or the GRE, where what they did was, instead of having their model look at the text that the question was asking about, they only trained systems to look at just the questions. And we've seen lots of other papers in this field as well. So lastly, we're going to talk about how we overcome biases and apply these lessons to real-world tasks. And here we're going to break this down into 2 parts. We're going to first look at how can we overcome hypothesis-only biases, and then we're going to try using those methods in more of a real-world setting. So the question here, the problem is that we've been focusing on natural language inference as an evaluation framework, but there still is interest and a need to also develop models to do this as well. So the problem is that if we have one-sided biases, if we have biases just in the hypotheses, this might mean that the models aren't going to learn the true relationship and they're going to fail to generalize. And there are lots of possible solutions we can throw at this problem. One is, let's try constructing new data sets. It's expensive and it also leads to more biases. Other approaches, let's just filter out the easy, or the examples that a hypothesis-only model can do well. So this doesn't scale well, and also people have shown that this doesn't really work to remove all biases, that there are other biases that the model may not find. The last solution could be, let's just forgo all known data sets with biases, but that's not realistic because data is always going to have this. And also some biases aren't necessarily always bad. Some might just be about typical world knowledge. And here we look at what's referred to as adversarial learning, and we can use that to the rescue. And this is work I presented at ACL in 2019, as well as StarSim this past year. And if we boil down the big model we had before, let's make it even smaller, make it more compact. This is our natural language, the components for an NLI model. We have the encoders and the classifier. Right? And the baseline system is training looks like this, where in order to update all of these weights, we basically pass the model, the predictions through, we make a prediction, and we backpropagate to update these parameters. So what we look here is adding a hypothesis-only classifier. So here we basically take a second classifier and put it on the right. And this classifier only looks at the encoder from the hypothesis. But what we do when we backpropagate to update our weights after the model makes an update or makes a prediction that was wrong or correct is we basically penalize our hypothesis encoder if our classifier does well when it only looks at this, when it only considers the second sentence. Because in essence what we're doing is we're telling this representation to ignore and overcome the biases. We're telling it to learn the biases so that this model can do well. And now that you've learned them, basically wipe them out and remove them.
So let me just like to clarify. So here the goal is to learn representation that are less biased.
Exactly.
Okay.
Right.
The
Because
representation of the sentences.
exactly. Because here we're still doing NLI here, and we're doing the adversarial NLI, but by punishing the encoder for the hypothesis when the hypothesis-only classifier does well, basically is our way of trying to encourage the encoder, the sentence representation, not to have that bias. And the second method we look at is we just don't use another encoder, but instead we basically just perturb some of our premises in order so that the relationship's no longer true. And for examples where we've perturbed our premise, when we backpropagate, we don't backpropagate into the premise encoder, but we basically backpropagate, reversing the gradient, to our hypothesis encoder. And the first question is what happens to model performance? So this is within one data set, we can see performance decreases. And this shouldn't be surprising, this should make sense, because here what we're doing is we're telling our model, don't learn a specific bias that's in the data. And now when we look at held out data from the same distribution, you're not going to do as well, but that's fine. And we experiment this on a synthetic example, where in this synthetic example, we shrink in our test, and we shrink in the problem when we say that two strings are going to be true if the first characters of the strings are the same. And we have another portion of this data where we can see there's an artifact where these are still going to be true, but they're just appended with a C at the end. And what we're going to do is we're going to train on this data set with the artifact and test on how well does it still learn the true relationship we want. And our results here indicate that as we increase our adversaries, the model does better on the held out data that doesn't have the bias, because these parameters just represent the strength of the adversary. We'll ignore that for now, but we can see when we have a weak adversary, we aren't learning the true relationship, and we're just learning this artifact, or this statistical bias. And then the question becomes, how well do these transfer to other NLI data sets? So for when we use a hypothesis-only classifier, we can see there aren't really decreases, but there are some small increases on some of the data sets. And when we use this negative sampling approach, when we perturb the data, we can see much variance in our gains. So turning now towards more applied settings, we're going to look at emergency need discovery. And this is using adversarial learning in emergency disasters to discover emergency needs. And this is in addition to fellowships that funded my PhD. Some of my research is also funded by DARPA programs, and this one's specifically for, it's called localized situation frames, where the goal here is to determine whether a tweet expresses an emergency need, and these needs is this defined set of categories, like is there unrest, or is there water, is there a water need, is there a food shortage, and this was really inspired by earthquake in Haiti, where what the situation is say we have an earthquake in a remote location, so not something like New York here, but a location where we don't have resources, we can't just use Google Translate, so we need to build up systems in a short amount of time in order to do these things. So the goal of the program was, how can we develop systems in half a day that can identify the topics that were in the text? And part of this program was involved working with human annotators, non-experts who spoke these languages. And I developed basically the system to interact with them. And there's a lot of crowdsourcing involved in this as well. And if you're interested in this is an interesting Vice article in 2015 about this program. So what we did internally was we collected data from 8 high-profile incidences. And these are all the incidences. And we had crowdsourced workers label how well the tweets, whether the tweets expressed any of these needs. And the model that I did was I just used a one binary classifier for each of these needs. And then I looked at using adversarial learning to remove, or basically to predict an extra attribute and remove that from the encoder. And the things I looked at was which disaster or event occurred. And one reason why this makes sense is because disaster needs, like a water shortage, might be described differently in different languages and in different situations as well. I also looked at who was the annotator that annotated it. And our experiments just used a round robin approach, where I trained on all disaster scenarios and tested on one held out one. And here we can see just how well our model did for different tests, for different of the events, for different needs. So this is utilities, and these scores represent the F1. And I'll just walk through these quickly for the different needs. And the takeaway here is really that adversarial learning can help each incident type, and we can see a small increase in F1 depending on the need and the situation that occurred. And I'll skip this for now. I've been working recently with a first-year PhD student on a project that's basically trying to explore the reasoning capabilities of models beyond natural language inference. We've submitted this to cognitive science, which is a cognitive science venue that's under review. And the idea here is basically we have these assumptions that we make about everyday life. Like countries have leaders, or presidents, people have parents, siblings, spouses, and we looked at whether fancier embedding systems actually capture these phenomena. And what we did was we basically gave these systems a sentence like a blank has fur and asked it to fill in the blanks. And if you're following this field, the names for these models are inspired by Sesame Street characters. So here we have the new one's called Bert. And these were the options that Bert gave: dog, cat, fox. And what we did was we made this even longer. So we said that a blank has fur, is big, and has claws. This is what it returned for us: cat, bear, lion. And we expanded it all the way out to 10 features. It got bear correctly. And we basically see that as we expand the features, our models were actually able to do surprisingly well, where here on the right is mean reciprocal rank. And we also did on the flip side, where we asked the systems to fill in the sentence. So we said, a bear has humans from some data that was collected. It said claws, teeth, cubs, paws. In the model, Roberta, a variant of Bert, said teeth, claws, eyes as well. And basically, just to conclude, this was basically what we spoke about today, was developing tests and using them to analyze inference capabilities of models, discovering biases in existing tests, and overcoming these biases and applying lessons to real-world use cases. And this really, I think, can categorize my research into these 4 topics: on computational semantics, multi-word representations, so it's like word embeddings, model and data sets analysis, and as well as applications. Today we highlighted these works. I was briefly mentioned, this is earlier work I had on creating embeddings that are based on larger context, which has become a very hot and popular thing in the field. And just looking forward in future applications, I'm very excited about the idea and ability to leverage text as data to broaden types of questions in other disciplines. And what I want to do as well is be able to push the linguistic unit of analysis beyond the word level, where when fields such as like political science use a lot of these NLP techniques, the unit of analysis is often limited to word level. So what I'm interested in is doing that and expanding it out to broader units as well. That I'd like to thank my broad collaborators. I've had a long list. I'm fortunate to work with great collaborators. This is a subset of collaborators whose work I presented here today. I just want to note that a lot of these collaborators come from lots of different institutions. And this is something I think that I'm excited about, not only continuing, but also leveraging for students, where students are going to go on to careers either in research at some of these universities or jobs in industry at some of these companies. And this is something that I think is really important, is how can we leverage these connections to help students as well, through internships and also for careers and job placements as well. So with that, thank you.
Any remaining questions?
I have a question. So when you build these data sets with reasoning capabilities, like what were the types of reasoning capabilities that you think the current system, let's say the BERTs and Roberta and all these like state-of-the-art model are still bad at capturing, and how would you go about enhancing the data sets for that?
Right.
Just curious.
Yeah, so one thing, part of why I like that work on these assumptions is that there's a lot of reason why we thought models wouldn't capture this. So there's this notion of reporting bias. And what reporting bias is basically saying is this idea that things that are common aren't expressed in text. Where if you see the phrase black sheep appears much more in text than the phrase white sheep. So if you had a system that basically was only learning from text and not learning from other multimodal experiences, you might think that these are examples that they wouldn't get. And that's what I like about this work on these assumptions, is that it's sort of beginning to look at, do models capture these types of assumptions? I think other phenomena that are really important are types of phenomena that we learn about through modes that aren't just text. So things like being able to maybe vision and grounding. So how can we understand or given an image in a text? That I think is really the next steps of where I want to take this as well.
Yeah, and then one that you mentioned about these events like Lorelei, which is the big event. I think one of the reasoning that seems not to be present is temporal reasoning. And how, I mean, I think none of these data sets contains that. How would you go about, let's say, if you want to go on and develop data sets that kind of capture these various, how do you go about?
So I know of actually a few data sets that deal with temporal reasoning, because that I think is a big question for the NLP academic community, because we often assume that we train these models once and now great, nothing's going to change, and when even the setups that we use don't capture that notion of temporal. But there are a lot of data sets now from dealing with relation extraction that capture temporality. And I think those are the types of things I want to include as well in this DNC vision too.
The example of the pun that you showed was really interesting. And it got me thinking, how would you encode or try to reason about text that its literal meaning is one thing, but what it actually implies is the exact opposite. Right? So something like irony.
Right.
So maybe like you have a really short paragraph of like a description of someone's day, right?
Yeah.
Maybe they're having the worst day ever. They wake up and they lose their credit card and they get to work. You know, whatever series of unfortunate events you can imagine. And then they get to work and someone asks them, "How was your day?" And they say like very dryly, like, "Great." Right. So obviously they mean the opposite. But like, how would you deal with something?
Right. So I think so even in your example, you included things that a system that only looks at text is going to fail on, like your tone, right? The way you said "great" was different. A system that's only looking at text can't see that. And I think that's like exciting about a lot of like Julia Hirschberg's work here is like dealing with that. How can we deal with tone and other things as well? About like metaphors and irony, so part of these JSOL workshops is in addition to like faculty and graduate students getting together to work for the summer, there also are a lot of undergrads. There was an undergrad who was really interested in like metaphor detection. And we spoke a lot about these like types of issues. Is how exactly could we then create a data set like this that focuses on metaphor and irony? Unfortunately, there's a lot of, so I mentioned these like shared tasks earlier, and these shared tasks are often, some of them are there are phenomena like irony and metaphors that are tested for as well. So they'll oftentimes just be viewed as like a sentence classification problem. So the system will get a sentence and they'll have to predict, was this metaphorical or was there irony in this or not? And that's something I want to include in this DNC. And I think what's really nice about this framework is that it really is a unified framework to test all these different phenomena. And something that I didn't speak about here, but I have experiments on that's interesting, is another question is, a lot of these phenomena are related. Right? A lot of these reasoning capabilities, a lot of these types of reasoning are related. So what we can do with this whole suite is like train on one type of reasoning and test on another to see how they're related as well.
Right. And again, in the interest of time, we should
Yeah, right there.
not try to elicit further questions.
Yeah, sorry.